see you're holding down the front row. Good morning. Appreciate it, even though it's a different face. All right, can everybody hear me? No? Yes? No? Okay. There's no consensus. Much better. Okay, well, welcome back, everybody. We'll continue where we left off. And where we left off was still on Chapter 4, Defects. Today we're going to transition to Chapter 5 on Diffusion, hopefully soon, after we wrap up 2D defects. Okay, and thank you for all of those that have donated your pennies, much appreciated. We will get to the demo come Wednesday on the Kirkendall effect. Okay, you can't see anything. Oh dear. 20 seconds. Bear with me. Okay, there we go. We're back live. Okay, right. So we left off on the discussion of ASTM standards and also how do we quantify the grain size number and also the number of grains. Clearly you can see from this micrograph that polycrystalline samples have different size grains. And of course we try to engineer them to be as uniform in size as possible. But of course there's always some distribution, and so we talk about the material using this grain size number, and it's related using this equation that you see here. And where we left off was I was discussing that you have to take these images at 100x magnification when you report this. Obviously, if you do it at different magnifications, that's fine. Obviously, in real life, people do their experiments at a variety of magnifications, and there all you have to do is just normalize to that. So if you do it at 200x, 400x, you just scale it by the square of the magnification. That is a detail that you're not responsible for, because at this level, you're just responsible for 100x magnification, okay? And how you relate the grain size number G to the number of grains in a 1 square inch area in your micrograph, okay? So I thought I skipped this. This is not on top hat despite the yellow. I thought I'd just go over this example briefly. You know, if you have to compute the grain size number G and you're given the number of grains. So in this example here, it says a polycrystalline aluminum sample is imaged at 100x. So that signals to you that it's collected at the correct standard magnification, and that it has 16 grains here, and then also in a 1 square inch area. So when you're asked to compute the ASTM grain size number G, because it's in the exponent, right, you have to take the log of both sides. And you may or may not have seen this already. For those of you that raise your hands, denoting that you've worked with the Arrhenius equation before, you may already be comfortable with taking the log of both sides, and that's all you do. So I've written out here the step-by-step process for you to review. So we'll go over it together. So you take the log of both sides. You can see here the exponent becomes the prefactor here, right? G minus 1 was in the exponent. So then if you move ln of 2 over to isolate G, you have ln of n divided by ln of 2, and that is still equal to G minus 1. And then if you move the 1 over, you see here, you've isolated the grain size number G. And then, of course, you can plug in the values. We know the grain size, the number of grains is 16. And then, so we plug that in for n. And when we solve the equation, we get the grain size is 5. I'm sorry, the grain size number. Yeah.
Not to hate on the whole complicated math method and all, but since this is 2 to a number, couldn't we just say, hey, 2 to the 5th, 2 to the 4th is 16, and go from there?
Yes, absolutely.
All be that even and nice, but
Correct. Yeah. So Kevin said, well, why couldn't I just like go in my head, 2 to the 1, 2 to the 3, 2. Yeah, you can absolutely do that because I gave you a really nice number for the number of grains, which is 16. You can absolutely do that. Right. If it's not so nice, a nice integer that you're given here, this would be the entire process. Yeah.
How would this change if the magnification was like 200? How would the problem change?
Yeah, so the problem would change because your number of, the number of grains would change. So you have to compute the new number of grains. We won't go, so it would scale by the square. Your n has to be now multiplied by the ratio of the two, so 200x divided by 100x, and that is squared because you're looking at an area. So we won't go into that detail, but if you want to go into depth, you can stop by during office hours. We can go through that. But I just don't want to dwell on that too much. Okay, the other method that people often use, in addition to just counting, and of course now we have software like ImageJ or any other proprietary software. Well, ImageJ is free, but if you have proprietary software that can count area and all that jazz, or you write your own code, fabulous. You can really get down to nitty gritty and have the computer do that for you, right? I mean, that's how we calculate like mass or area of a country, say, right? We have global images and we can let the computer do that job for us. The other way you can do it is just that you can write, you can just draw a random series of lines, I kid you not, and just say, okay, well, if this is the line that I draw, right, how many grains do I pass? And I just divide that to get the average grain diameter. It's just an averaging, right? Or if I go through this way, because of sort of the stochastic method of it all, of nucleation and growth, this direction will yield another average. So you can see there's quite a variation in describing the grain size if there's a wide distribution like you see here. I mean, clearly this grain is larger than this grain, and just randomly it's a little bit larger than this one, and this is smaller. So really what we're going for is an averaging effect. Yeah. Yes. I would say this is low res. So the way these micrographs are taken, it's just by the reflection of the light. So if there are void spaces in between the atoms, they reflect differently. That's how you get these sizes. So my guess is, there was some random void there, that reflected the light differently in the optical microscope. To be honest, I'm not exactly sure what the exact conditions are of this. So it could have been that there was a dust piece that was there. Somebody maybe spat on. I have no idea. Obviously, if you're reporting to ASTM, you would take quite a lot of care and not do any of that. But in terms of just whatever those conditions are for that day, it could be anything. But really, the contrast is related to the reflection of light coming back to the surface. That's all it is. So it's an indication that it's not perfect. Okay. And yeah. Oh, sure. Oh, it's just the number of grains along L, that distance. That's it. So you just count. Yeah. Okay. Right. We won't go into twinning too much, but it is a really big area of research in terms of understanding how atoms between grains line up with each other. So what the examples I've shown you before, the atoms can be oriented in whichever way. And in the nucleation and growth example that I showed you, when you have a few atoms and you're solidifying, you have a few atoms start to nucleate and crystallize, the orientation of those crystals aren't always in the same direction, right? And there's a particular case in terms of area defect where they do line up perfectly, but just at an angle, from a particular angle from each other. So that's the example that you see here, where you could see the crystal growth in this direction is aligned just like this, right? And you can see that there's a misorientation in this area above the twin boundary or just on the other side of the twin boundary. So you could see how the two crystal structures are related, but at a particular angle. So we call that a twin boundary when the crystals are just twin. They're mirror images of each other right at that grain boundary. And that twin boundary could be a few nanometers long. It could be a few microns long. Any larger than that, I can't really think of an example, but you could see that there could be this sort of perfect misorientation, if you can call it that. And these twins actually have significant implication when it comes to reactivity and and also strengthening of materials. And there's a lot of ongoing research here at Ohio State to understand what happens when you have a twin boundary like this, and you may or may not be working for a professor who does that already. But I wanted to show this example. A lot of people are working to actually image and really track down these twins. And you could see here in real life example, this is a platinum nanoparticle that's been 3D reconstructed, and this is pretty recently. This is done recently, and what's really cool about this image, which may not be so apparent given its fuzziness, is that these are columns of atoms, and this happens to be from a website from UCLA, but we do a lot of work here, and a lot of universities do this work too, where you could image the twin boundaries. You could see quite a number of twinning. And so this particular particle, because it's platinum, it's used for heterogeneous catalysis. So this is huge in chemical engineering, systems engineering, for automotive applications and a number of purification applications as well. But the atoms that's right at the twin there, because there are voids that you see in the figure in your book, those atoms are less stable in terms of relative to the atoms that are in the bulk, so to speak. So these atoms that are at the surfaces are more reactive. They have dangling bonds. They want to react, and your reaction will drive forward either at a lower temperature or at a higher rate of conversion. So this is extremely important for all the automotive companies and everything else that that pertains to heterogeneous catalysis. Okay. And all I mean by heterogeneous catalysis is that the catalysis happens with 2 phases. So 1, your solid catalyst, and 2, you have a fuel that's coming in. Either it's your exhaust from your car that's like carbon monoxide, and you have to react that to CO2 so that your car meets emission standards, that sort of thing. So you have the gas phase and then your solid catalyst, so that's heterogeneous catalysis, okay? That's it, but that's beyond the scope of this, of chapter 4. But it's a pretty important example of why we study twin boundaries, why we try to image them, and why we care about where these atoms are. And if you watch that YouTube video, you'll see that they can actually rotate this entire particle and map out every single atom that's in this particle. And it used to be that you would just image and you would get 2D projections of this particle. And now you can just rotate 3D and reconstruct. That's very cool. And beyond very cool, it's scientifically advanced. Okay, non-crystalline. We talk so much about crystalline systems, and then what happens when crystalline systems have one defect here or a line defect there or mismatch of orientation and have grain boundaries. Now we'll talk about the entire system not having any long-range ordering at all. Forget the BCC, the FCCs, the simple cubic, the HCP, forget all of that. What happens when you have a material that doesn't have any long-range ordering? How do we talk about it? Well, we still talk about it in terms of structure, right? So when someone scoffs at you and says, well, glass doesn't have any structure, clearly they have not appreciated the local structuring of silicon atoms around oxygen to understand how glass behaves. Okay, so you can share with them your knowledge and bring to them the joy of understanding glasses and disordered materials. There are many things that can be called glass. Obviously, the everyday thing, household items that you have, right, that are glass, made of a silica, right, SiO2, that's definitely glass. But we can also just classify anything that doesn't have long-range ordering as a glass. And that includes metal elements, and we'll get to that in a little bit. Okay, so it doesn't always have to be a ceramic material, okay, to be a glass. And you can see the atomic packing there. And then when we talk about, okay, how does that affect the energy diagram that we've been thinking about in terms of energy versus the atomic radius? Well, here to compare with crystalline packing, you could see that the equilibrium distance between two atoms, right? We talked about having E, and then this is R naught. We also call that A naught. Basically, the equilibrium bond distance, right? It's the lowest energy point. But can you have a metastable system? That means it's not thermodynamically stable, so that's not energetically stable, but can it still exist for a long time? Absolutely, right? I mean, we talked about diamond. That's a metastable phase. You have to produce it under high pressure, over high temperature, over a long period of time, right? So eventually your diamond is just going to become graphite again. I mean, that's the thermodynamic. It's going to take thousands and millions of years, but that's the, you know, it's a metastable phase, but it exists, right? People buy it all the time. So it's certain, so metastable phases can exist. Just because it's a little bit higher in energy of a system doesn't mean it can't exist. And that's the same thing for glass. So the equilibrium energy, or the, I should say, since it's not equilibrium, the average bond energy or bond distance, right, is a little bit farther, and that's drawn in this schematic here. So the bond distance is a little bit longer because, you know, the structure is a little bit more open. It's a little bit higher in energy, and that's denoted by this arrow here. You can see the energy relative to its crystalline counterpart is higher, but that's okay. It can still exist. So it's a higher energy, it's a complex structure, but that's okay with us, okay? And then when we think about how does it affect the volume change, right? When you think about solidification or crystallization, in ordered system, you have this liquid state, and then it goes through a transition, and now you have an ordered state, right? You have nucleation growth, and then you have this crystalline, beautiful, perfect state. So if you look at the volume, so that's normalized by the mass. The specific volume is normalized by the mass that you have. You go from some volume, right? Your atoms are just flowing about. And then let's say you have this instantaneous, precipitous crystallization or solidification. Your volume drops because everything gets, right? Now all the atoms are close together. They're packed in whatever crystallography, you know, crystal structure that we have. Okay. In glasses, it's a little bit different than that. Because they don't crystallize, right? We don't expect them to go to some close packed structure. What really happens is it undergoes this period between the melting point, TM, and the glass transition temperature, right? That's a new term. So it goes through this what's called supercooled liquid. So you're just cooling it down, and it's in this area that's just called supercooled liquid. It's still sort of, you know, liquidy, viscous, and then it goes through a temperature that's called the glass transition temperature, and the temperature drops. The specific volume drops by a bit, but you could see the takeaway message is that the volume, the specific volume that your material takes, that your glassy material takes, is still larger than that compared to its crystalline counterpart, just because it's not packed in, right? It's disordered, there's a lot of voids, there's a lot of defects. There's no long-range ordering, so the volume is different. Okay. And this can be seen in polymers as well, not just ceramic glass or anything like that, okay? And if you work in polymers already, you probably, TG is probably, this is not the first time you've heard of the term TG, right? You deal a lot with this, and you look at the phase transition in polymers, and you look at the TG of different polymers. Okay, so we will, oh, actually, you know what? I think this is actually not loaded. So we'll just discuss it as well. But I've sort of gone over this point that glass density is just less dense. It takes up more volume than its crystalline counterpart, okay? Yeah, this is not loaded, so I won't open up Top Hat. Okay. I'm sorry? Maybe. Okay, so amorphous metals. I've alluded to the fact that glasses don't have to be just, you know, this ceramic materials that you know about, silicon dioxide, right? And so William Johnson at Caltech back in the day Who's heard of vitrolloy or bulk metallic glasses? Ish. I see a sort of an ish head. Okay, I see. Has anyone played golf? Okay, all right, wow, a much larger percentage. Have you heard of bulk metallic glasses to be used in golf clubs? The buzz on the green. No? Okay, no, okay, maybe not. All right, well, there was a buzz on the green that whether or not professional golfers should be allowed to use metallic glasses in their golf clubs. And you'll see why this can be an advantage in just a little bit. So metallic glasses, as I've said, glasses can be made of metal. So what happens when you combine a whole bunch of metals together? We've talked about the Hume-Rothery rules, where if you have, similar atomic radii, similar electronegativity, the same valence, right, that you can form these solid solutions and they mix well and they crystallize well. Well, the alternative is you have a bunch of elements that don't satisfy any of those rules. They don't mix well, they don't crystallize, and you actually get increased stability. So here's one example. It's called vitrolloy 1. And you can see the atomic percent distribution here. You have 41.2 zirconium, 13.8 atomic percent titanium, 12.5% copper, 10% nickel, and 22.5% beryllium, atomic percent beryllium. Right? Why in the world would you want to mix all of these together? Well, it turns out this forms a beautiful metallic glass. And it used to be called bulk, well, it still is called bulk metallic glasses because people were trying to make it in bulk. You can always have some tiny amount that you can crystallize, but the trick is, can you make it in bulk? Can you manufacture this so that you can sell it? The issue with making bulk metallic glasses is you can think about it. Whenever you have these systems together, they do want to actually crystallize. Maybe the copper and the nickel will find each other and they'll form some crystalline phase that we talked about here. And then the titanium and maybe the zirconium could get together because they're both HCP, and then they'll form a phase. That's what you don't want. You don't want phase separation. You want it to be one homogeneous phase, right? And so the way you do that is when you're solidifying, you just drop the temperature really fast. And when I say really fast, I'm talking I'm talking about like 1,000 Kelvin a second. Can you imagine cooling anything that quickly? Yeah, it's really difficult to remove heat from any space, right? You're a mechanical engineer. You've had thermal transport and all of that. You understand how heat works. It's really difficult to remove heat from a space very quickly. But William Johnson figured that out. And so if you think about bulk metallic glasses being able to withstand, being stronger, having higher strength, you could think about using it in things that you'd probably dent a lot, like your watches or your phones that people drop a lot, right? You want it to be dent resistant. And so, patents have been filed. Apple has a patent on this. Is it in your phone yet? No, and that has a lot to do with international patent laws that will not be covered in this class. But maybe, 2021, I don't know. Okay, I pulled that number out of nowhere, okay? It's just in the future. I don't know anything about, patent law. But anyway, okay, and so you can see here the advantages of making bulk metallic glasses. This is the advantage of making a material glassy, right? So the strength here for glassy alloys, you could see it's quite high, in the 2,000 megapascal as compared to your traditional steels and titanium alloys. Wood is on there as well. Wood is strong, but not that strong. And then, of course, you have polymers, which, of course, based on their structure, you don't expect that high strength relative to that of the steels, right? The other thing to note is that because they're not crystalline, their elastic limit rivals that of polymers that you see here. So this is the range. So not only does it have high strength, but also high elastic limit. And so that can do a lot for us in terms of incorporating into materials. Okay, so this is just some background on how one makes a bulk metallic glass. The trick is, and we'll talk about this in just a little bit when we get to chapter 10 and kinetics and heat treatment, is that you just have to drop the temperature really fast to beat crystallization. And it will make the material tougher and stronger and more fracture resistant, which is, of course, advantageous for a variety of things in our lives. Okay. I've already discussed that in detail. So let's see. Let me switch. Okay, let me just go to that. One moment. Okay, let me switch back. Okay, well, it has decided that it wants me to put this in. No problema. Okay, so what you're about to see is two ball bearings, stainless steel ball bearings being dropped onto stainless steel, and you can see how it just drops. Let me dim the light. Okay, and now you see a ball bearing on a bulk metallic glass surface. So it's not a crystalline surface, and the bulk metallic glass is just right at the top of that base. Okay, so you can see the ball bearing is going, it's bouncing, and the length of time that it's bouncing for is, immensely longer than that when it was dropped on a stainless steel, right? And stainless steel is just iron, carbon, and some chromium in there, okay? We haven't discussed at all mechanical properties, but any guesses as to why this is? Yeah, so it is as solid, and it is more elastic, and the elasticity has everything to do with the energy transfer of the energy of the ball bearing hitting the surface. So in stainless steel, if you think about an iron crystal, right, with some chromium in it, it's crystalline. And so when we discuss in mechanical properties and also later in kinetics, we're going to talk about what's called slip planes. So when you have these defects, we sort of alluded to it when we were talking about line defects, right? These lines moving along. Well, when you have the absorption of the energy absorption of the ball bearing coming down to the stainless steel surface, that energy is transferred to your stainless steel that's below, that's just sitting there. That's the surface that's being in contact. Whereas in the bulk metallic glass system, when this ball bearing hits the bulk metallic glass system, it really can't defect it as much, right? There is no crystalline direction for these atoms, for these slip planes to occur because the entire structure is disordered, right? So it all goes back to crystallinity of materials, and also how when you have a disordered material, you can actually stop dislocation, because the dislocations that we've talked about, you need a plane, right? You need grain boundaries for it to occur at. And so when you don't have this, there's very little energy transfer, right? So it can keep on bouncing. And so when people try to incorporate in golf clubs, you could think about the ball coming in and just going, right? I mean, you'd have to increase your golf fields, no, but courses, yeah. You'd have to, make your golf courses larger or longer or what have you. And of course, if somebody can't afford, well, I doubt professionals can't afford bulk metallic glass clubs, but it sort of provides an advantage that's not inherent to the athlete, right? But of course, one could discuss what is inherent, what's not inherent, but that's for another class. Okay, let us move on. Okay, let me see. I'm just going to wrap up here in chapter 4 so that we can move on to diffusion. But remember, crystalline materials, while they're great and we need to understand them and understand the formalism so that we have a way of speaking to each other and describing and characterizing materials, defects are fabulous, and they occur in a number of ways. Okay? All right. Let's now move on to diffusion. Okay, so you have a defect or you have an atom, right? Most of the time, the static structure, right, we understand how that works. We understand what happens when there's a defect in some static state. Now what happens when these atoms or these ions start moving, or we want to intentionally introduce a gradient, a concentration gradient in our system? How do we understand the flow rate of this atom? And there are a lot of processes that we want to understand because they make our material stronger, or we want to detect some flow rate in biological materials. We're going to need to understand diffusion, and we're going to need to understand the Arrhenius equation again, but in a different way. Okay. Right, so chapter 5 summarizes the discussion of diffusion, and so we'll cover those discussions, and I'll go into detail, how to deal with examples when you're trying to understand thermally activated processes, and also when these point defects move, or when how they're made. And then we'll talk about differences between steady state diffusion when your flux isn't changing, and then non-steady state diffusion, which is when your flux is changing as a function of time, right? Those really are the two major points of discussion when people talk about diffusion, and so we'll go into that. All right. Given that there are a variety of students and backgrounds and interests in this class, I'll try to touch upon why diffusion is important and interesting in a different number of applications, right? Certainly we've talked about alloying. When you incorporate another element into the system, right, you want to understand how long is it going to take for the alloying process to reach equilibrium, right? If you're flowing some sort of gas through and heating in high temperature, at high temperatures, how does that affect the material? You want to understand the rate of including that second element. The flip side is you can also think about environmental degradation. When your material is exposed to elements, it's going to go through oxidation. It might go through hydrogen embrittlement. It might go through nitrogen embrittlement. If there's salt water, if your beam is in some saline solution in the middle of the ocean somewhere, right? You need to understand how that oxidation process is going to affect the structural integrity of that material, right? And so here I provided some example. Someone asked about Damascus steel, and so I thought I put it up an example here, why we're so interested in it. It was one of the early examples of diffusion at its best and strengthening of an iron bar that somebody found, right? They learned how to, around 500, the year 500-ish, right? People learned how to strengthen materials by incorporating carbon. Now we call it carburization. Now we call it strengthening, right? Now we have complex phase diagrams called the iron-carbon phase diagram that every single material scientist is going to learn about in chapter 9, right? So we have all this knowledge now, but in the year 500, people stuck, iron in like some ashy pile of burning wood, and it came out really strong, and they defeated their opponents, and they won some wars, and all was well, right? There wasn't really a formalism, but it was a good example of diffusion. So basically the carbon in this pile of ashy wood was carburizing the steel, was carburizing the iron rod, and then making it stronger, iron carbon, right? So we'll talk. So that was a good example of how to strengthen material through the process of diffusing carbon. Now, why it's called Damascus is because it was imported into Damascus and then exported out of Damascus, not originally from Damascus, thank you very much. And that was from a very lengthy study that was done a few years ago. And people have since then tried to copy this method. If in 20-something, can we back out and track the microstructure and also understand the amount of content in carbon and basically reproduce Damascus steel in present day? It's actually difficult because one could just say, well, why don't you just digest the Damascus steel and just do elemental analysis with the equipment that we do have? The problem is destroying artifacts and historical objects is actually quite unethical. And so, using our knowledge of material science, we can actually engineer what we think is a concentration and then sort of back out, some structure that matches this So we can do it both ways. We don't have to destroy materials just to know what's in it. Gas storage, diffusion, right? If you're storing hydrogen in a tank, you really hope that tank does not leak out hydrogen, right? For a number of reasons, safety, explosion, all of that. But also, if you have hydrogen stored for, let's say, hydrogen fuel cells, right? Because you're working on renewable energy technologies, you want to have a safe way of actually storing it, and you want, beyond safety, you just want to contain it, right? But it's extremely difficult and challenging because hydrogen actually corrodes materials, and so you have to come up with a formulation that doesn't let hydrogen diffuse and corrode a gas tank, and hopefully it doesn't end up looking like these very rusty gas tanks that I would definitely not get close to. Diffusion, energy storage. If you want to understand how atoms and ions diffuse, that will be immensely helpful when you're trying to, let's say, revolutionize the geometry of batteries altogether. Currently, they're using liquid electrolytes, which, as we all know with the Samsung phones, how that could end up, right? But what if you took out flammable liquid electrolytes and replaced it with solid electrolytes? Now you have to understand how ions move in the solid form, how ions diffuse from one electrode to another electrode, right? So solid electrolytes also use, you know, the foundation of diffusion. And then you could, you know, also think about not just diffusing atoms and ions, but you could think about diffusing molecules. If you're designing a breathalyzer, what are you diffusing? You're detecting ethanol, right? Or some derivative of ethanol once it has reacted with saliva and all of that, right? If that's what you want to detect, maybe you have a membrane, right? And so if it goes through the membrane, how do you model that diffusion rate? How do you model that flow rate? So diffusion, regardless of what engineering discipline you're in right now, has a lot of applications, and you know, and it's all based on the same concept of a thermally activated process. Okay, speaking of thermally activated process, we revisit our friend the Arrhenius equation, right? Typically, it's some rates, and it's related to some activation energy Q divided by RT. So the T is your temperature in Kelvin. And here I write C as some proportionality constant. It could be anything, really. But that's just it. And the typical curves or plots that you see when it comes to the Arrhenius plot, it looks something like this. It's usually plotted as a linear curve. And here in the y-axis, you see the linear, the log of that rate. And the x-axis is typically shown as 1 over T times 1,000, and that's inverse Kelvin. So what does that mean? That means whatever your temperature is, here on the x-axis, you take the 1, you multiply it by 1,000, and then you divide by your temperature. Oh, sorry. I got that backwards. I was doing the upper axis. Right, you take you take your temperature. If it's 1,000 divided by your temperature, that gets you your x-axis. You may or may not have seen this before, but I think it's a little bit difficult to like divide the temperature and then look at the x-axis and then go backwards. So a lot of times the temperature scale will also be reported up here, and they are equivalent. So 300 Kelvin is about 3.4, something like that, times, yeah. Is that right? Right, yeah, so 1,000, so it should be 1,000 divided by your temperature, 300, gives you 3.3-ish, 3 1/3. So that's how you convert between the two. So in looking at this plot, you see then if you treat this as a y equals b minus mx, you could see where the linear relationship comes from, where x is inverse temperature, 1 over T, then your slope m is your activation energy divided by the gas constant, and it's the negative of that, so it's a negative slope. The only thing I would be very careful about, and also why this is in a dashed line, is how you treat very high temperatures. So 1,000 divided by a very large number, right, very large T, will give you a very small 1 over T. Now, what does it mean when you get to really high temperature? You have to be careful that in this linear regime, what you're looking at is actually one mechanism. So if an ion is diffusing along or something's being activated, vacancy hopping, atoms hopping, what have you, right? That's one type of process. When you get to really high temperature and really low 1 over T, you have to be careful that you're still in the same regime. So if you get to really high temperature, what does that really mean, right? What does 3,000 Kelvin mean? I mean, that's extremely high. For a lot of materials, that's basically at the melting point, if not well above the melting point, right? And so atoms behave very differently in the solid, well away from its melting point, versus near its melting point, and of course, after it's melted, it's in this liquid state, and it doesn't behave the same way as in the solid state. Okay, so you really should be careful that when you extrapolate this ln of C, that, you know, mathematically, it's just a linear equation that, you know, you're all familiar with, but physically, it's a very tricky way of describing your solid system, right? So what typically happens is people don't actually plot this area, they just end like right there. Okay, you plot it to some high T where the diffusion mechanism is the same, and then you just stop. You just don't measure anymore, because the closer you get to the melting point, the more differently your atom behaves, and it doesn't capture the real physics of the system, right? So it becomes non-physical. Then you're talking about visco, you're talking about a different regime, okay? So that's what I want you to just take away from this plot is, yes, you can definitely do a mathematical extrapolation, but like 1 over really high temperature, 3,000 Kelvin, is totally in a different regime if the melting point is well below 3,000 K, okay? Just a note. Okay, so we'll do an example together where we can just look at the rate of oxidation. The way you deal with these types of equations when you're given an unknown, you could write your set of equations, okay? So here, some rate, in this example, it's oxidation. And we're gonna look at oxidation rates at a variety of temperatures. So if you're given that the oxidation rate of a metal is 1.05 times 10 to the negative 8 kilograms per meter square, meters to the 4th second, so that's the rate, okay, at a particular temperature of 300 C. And then at a different temperature, let's say 400, it's at a different rate, right? And you're asked to determine the activation energy Q. Well, we know everything except for C, right? We know the rate, so the rate at 300 C or 573 Kelvin, right? It's just C times exponent of something that we don't know over right, so we know how to write these relationships based on the equation. And we also know the rate of 400 C or 673 Kelvin. And we know it's activated, it has the same activation energy. Right? So when you have this set of equations like this and you're solving it for an unknown, right, how does one tackle such a thing? 2 equations, 1 unknown.
Can't you just divide the first equation by the second equation and then that eliminates velocity and then you can just solve for Q from there?
Yes, what's your name? Nick. Okay, so Nick suggested that you just divide the 2 equations and the C's will cancel out and solve for Q. Absolutely. That's it. That's it. So you can definitely write in this rate, which is 2.95 times 10 to the negative 4th. And this one is 1.05 times 10 to the negative 8. And you divide that. Now, what you're left over is going to be some number, right, once you do the division, equals, I think in my example, I actually have it upside the other way. I have 2.95 times 10 to the negative 4 divided by 1.05 times 10 to the negative 8. But really, you can just divide. So then you have exp and you have negative q. So now you could do something that looks like this. Okay? And you take the log of both sides to solve for q. Now, I just want to jog your memory, right? If you have something that looks like this, e to the x, e to the y, you could just do e to the x minus y. Okay? So that's where this comes from. Okay? Log of both sides, and you get the answer, which I believe I've already typed up and included in your lecture slides, but I wanted to go through it slowly with you so that we're clear. Okay. Yep, okay. Unfortunately, I'm going to have to do this. Okay. It's a much clearer way. So that's basically what I did, what Nick said, right? Just divide the two values, and you get that. And then you do e with your prefactor to the exponential, right? And then when you log both sides, you get this relationship, and you can solve for q, or if you convert to joules instead of kilojoules. Okay, so that's how you solve for the activation energy when you're giving two rates at two different temperatures, but they have the same activation energy. Yeah?
How did the 673 and 573 Kelvin go from being on the bottom of the first two equations and then being multiplied by Q over R in the
Yeah.
divided form?
So this is for simplicity, okay? So if it's 1, okay. So it's still divided by, so the 673 is still below. Do you see what I mean? It's not 673, it's 1. I just separated the 1 out. So, okay, I'm glad I cleared that up. Okay. So, when we talk about activation energy, this is it. It's just a hopping mechanism. It's going from one site to another. So you see here, whatever energy state it was at, it has to overcome that. And it could be bond breaking, right? If it's going through a vacancy type of diffusion mechanism, it jumps through another vacant to a vacant site that we talked about. It has to overcome that energy to then go to another site. So when we talk about, before, let's say sites with, let's say this is a vacancy right here. In order to go from here to here, here to here, right, there's some energy costs. And that's what your activation energy is. And so that's what this diagram is just showing you. So just intuitively, you think about, okay, if activation energy is lower, it's more likely going to happen because in any sort of particular state of the system, when you're vibrating, at some point, just statistically, you're going to have enough energy to overcome that. And so if you crank up the temperature and you're putting more energy into the system, you're allowing for that rate to be higher, which we've seen from the example, where the rate for the lower temperature is much lower than that of the rate of the higher temperature. Okay. And I also want to note that if you look at the rate, this is at 300 C. Okay, this one is at 300 C, and 2.95 times 10 to the minus 4 is at 400 C. So you could see that the difference of 100 degrees is not proportional. It's not proportional. You could see that it's going from -8 rate to -4, 10 to the -4, right? So it's a huge increase even though you've just gone up 100 degrees Celsius, right? So you could think about, well, what happens when we increase, temperature when we're trying to carburize, right? And you want your rate to be faster, just increasing the temperature a little bit will actually get the rate to increase by a lot. So you can get your carburization done in a much faster time than if you had sat at a lower temperature. okay, in terms of processing. Okay, so in the last 4 minutes, this will be a top hat question. So it asks, what is the rate of oxidation of a metal at 500 C if the activation energy is what we calculated, which is 328 kilojoules per mole? And here I wrote, again, the rate for 300 C. So the question asks you to actually put in the answer. So you could put in the answer as, 3 sig figs e to the something, e to the number. And so you could write it just like this example, okay? Exponential, e to the something. Yeah, that's what it means. All right, I'm increasing the time. And based on the example that we just did, you can also just self-check yourself to see if the value that you get makes sense in terms of the increase in the rate.